Hello everyone, my name is Rafael Meier. I am from Federal University of Santa Catarina, Brazil. The current work was developed in LabSat research group, which deals with combustion problems and issues related to biofuels, energy generation cogeneration, as well thermal systems performance. So in this presentation, I'm gonna talk about detailed numerical simulations of laminar premixed flames, focusing on flame flow interaction in a slot burner experimental configuration, where will be approached some topics of flame hydrodynamic theory. The presentation is divided in 5 main sections. An introduction where the primary goals are presented. Next, we review the big picture of theories where the main parameters are addressed. Then we take a look at the main features of computational methods. Further, the results are shown, and I will give a summary with our main considerations. The increase in energy efficiency and fuel flexibility requirements for IC engines and gas turbines have pushed the development of premixed mixed combustion devices to work under higher pressure, higher temperature, and linear mixtures in order to produce less carbon dioxide and reduce the harmful emissions like soot and nitric oxides. So in this scenario, this work turns to simulate the interplay between flow and premixed laminar flames, in which their geometries and structures are analyzed in a slot burner configuration. Then the focus here are: estimate the flame speed in the laminar stretching regime for stoichiometric and lean reacting mixtures, developing and testing algorithms for premixed flame simulation and tracking, analyzing the flame kinematics under different definitions of the location of the flame sheet, observe the effect of flame curvature in local stretch rate, displacement speed, transport, and reaction within the flame. The flame speed is one of the staples of combustion theory. It has a precise meaning when the flame is planar and propagates steadily, because the mass flux through the flames is constant and uniform. For 2D and 3D flow, the flame speed is not uniform. So the flame undergoes a continuous stretching, which affects the transport rates and results in a non-uniform burning rate. In the scale of fluid flow, the flame shrinks to a sheet in which it's assumed that the fluid properties jump from cold to hot state. This means that the flame thickness is a boundary layer that moves with velocity Vf. Then the flame speed can be computed by the difference between the absolute velocity of flame front minus the incoming gas velocity. But if you apply a zoom in and take a look at flame region, we see a coupling between flame structure and fluid mechanics. The flame has a thin thickness that forms its geometry, and it can be deformed or stretched with the fluid flow interaction. However, this definition of flame geometry becomes ambiguous unless some property of the structure be identified as a reference frame. Here in the first item, we point out that the flame front can be represented by a mass fraction of any species I. So, in thin flame approximation, the flame can be associated to some species mass fraction. As illustrated in figure A, since the fluid flow acts in this geometry causing a variable or a constant deformation, the stretch rate is defined as the rate of flame surface element deformation. Looking at figure B, the stretch mechanism can be divided into components: a tangential deformation due to fluid strain rate, and the local displacement speed times the divergence of the normal isosurface defined as the geometry curvature, kappa. The local flame speed in the flame-flame approximation is a linear function where the perturbation of the flat flame speed is related to a linear coefficient, this fancy letter L, called Markstein length, and the local flame stretch. To facilitate the analysis, the local flame speed equation is dimensionless and is normalized in relation to the flame thickness and flat flame speed which gives rise to the Markstein number and Karlovitz number. From the definition of thin flame approximation, the isosurface can be defined by some flame structural property. The normal of the front is the gradient of this property divided by its modulo. So, the normal of isosurface can be used in the conservation equation for species mass fraction. This gives rise to the definition of local flame displacement speed St. The two last terms are related to reaction rate and normal diffusion, which are present also in flat adiabatic flame. However, shows up a term related to tangential diffusion responsible for the flame deformation. For meaningful comparison between values of the displacement speed at different locations, St is often normalized by the ratio of local density to the density of the incoming gas. This is called the density-weighted flame displacement speed, which can be directly compared to the planar flame. Some details of direct and macro simulations are present. In DNS simulations, you can solve all conservation equations without any model. So here you use EBI DNS, which was developed in 2012 at Engelbert Institute at Karlsruhe Institute of Technology. It is implemented in the open source code OpenFont, which is coupled with the well-known Cantera library. Cantera is responsible for computing the transport properties derived from kinetic gas theory. The solver uses the finite volume method to solve the fully compressive Navier-Stokes equations for reaction flows. For this problem, since you are turned to the problem physics, a rectangular structured mesh was used, providing at least 30 cells to solve the laminar flame thickness. The simulation was carried out in a two-dimensional X-symmetric domain with height of 20 mm in the streamwise direction and 5 mm of width. A Poiseuille velocity profile is imposed in the half of slot inlet where the reacting mixture is incoming, and zero velocity is enforced in the remaining phase where air is present. So, some important definitions used here are: the simulations were performed at atmospheric conditions, which avoids the chemistry of low temperature combustion at flame inlet. The behavior of two fuels were studied, methane and DME, which can be produced from biomass. To look at the effect of stretch in flame structure, two different isosurfaces were chosen in different regions. The first one represents the flame preheating zone, considering 90% of the unburned fuel mass fraction, and the second one, the reaction zone, which the isoline is taking the maximum heat release rate for the fuel mass fraction. This table below presents some simulation features. Two stoichiometric relations for both fuels were considered, for phi equals to 1 and E equals to 0.7. The laminar flame for DME is in general higher than methane, which impacts in the flame thickness. The Lewis effective number was computed for the mixtures, where methane has a Lewis near 1 and DME flame presents a Lewis number above the unit, so both mixtures hold a stable flame. Besides, the table presents the mean velocity for the Poiseuille profile and the values for the fuel isosurface for each case. Looking at figure A and B is seen the isolines for flame temperature and fuel reaction rate. Some visual conclusions about flame deformation can be inferred. In figure A, looking at the base, the isolines are more spaced. The graph C applies a zoom in on this region. The burning rate slows down since the effects of fuel dilution and heat losses increase in lift-off region. On the other hand, the opposite happens in flame tip. In figure A, seems that the isolines are being squeezed by heat concentration. Compared to figure D, the fuel consumption reaches its maximum value in this region. Therefore, there is a focus effect of heat in the tip of the burner, leading the preheating of the unburning mixture, increase the reaction rate further. The flame has a more flat profile in the intermediate region between the base and the tip, which the reaction rate is uniform. The direct comparison between fuels show that DME at stoichiometric mixture in figure C presents the higher laminar flame speed, resulting in a thinner flame, shorter cone, and smaller lift-off distance. As the equivalence ratio is reduced to 0.7, the flame thickness and lift-off distance increase, more for methane than for DME. The flame tail is also displaced to a position farther from the slot half width, resulting in fuel leakage and air entertainment. The elements of flame fin approximation are brought up in this frame. So, in figure A, the Karlovitz number is plotted versus the normalized arc length from the isosurface that represents the reaction region for methane at stoichiometric condition. Besides, each component of stretch is shown explicitly. The strain and curvature effects are both positive and equivalent up to 0.7 in arc length axis. Near the tip, the strain effects becomes positive and curvature negative. Since the curvature is dominant at the tip, the sum of both effects is a negative. The stretch rate definition in the reaction zone is more sensitive to variations in flame curvature, and therefore will be used for the remaining analysis. The graph B shows the normalized displacement speed for the reaction zone for both fuels, at both equivalence ratios. Both fuels present the same general trends, indicating that the curvature term prevails, and also because the diffusive relation between fuel and oxidizer keep flames stable. The stoichiometric flames present steeper gradients and a larger variation than the lean flames. Near the tip, the methane flame presents a larger positive deviation from the laminar planar flame speed as a result of the larger curvature. In the second row is shown the correlation between the normalized displacement speed to Karlovitz number. The general trends are: near the base, the Karlovitz number tends to 1 and the displacement speed is smaller than the planar flame as consequence of positive curvature and heat loss to the burning ring. Towards the tip, the Karlovitz number becomes negative due to negative curvature and the displacement speed increases in respect to the planar flame. The stoichiometric flames present sharper tip and therefore reach large values of Karlovitz number. The structure of two-dimensional flame is affected by the tangential components of convection and diffusion fluxes, disturbing its original arrangement. In the last frame of results, it looks at the normal flame distributions for methane flame at stoichiometric condition. In the first row, it is plotted the normal distributions of hydrogen and oxygen mass fractions as well as the temperature profiles. In the second row, in graphs D and E, is shown the normal distributions of the hydrogen and oxygen reaction rates as well the heat release rate and volumetric energy diffusion in figure F. The curves correspond to two positions along the flame surface, one around half the flame height, where the normalized displacement speed is 0.83 and curvature is positive in red lines. The green lines represent the negative curvature, the position near the tip, where the normalized displacement speed is 1.45. The dotted lines are the Cantera results for the planar flame. The plots are centered in maximum heat release rate, and the triangular markers identify the position of the flame surface for the previous definition of the preheating zone. So, observing the graph A, the hydrogen profiles for the positive curved region presents a deficiency in the preheating and post-reaction region. Both the production and destruction rates in the figure below are reduced. The oxygen mass fraction is not strongly affected, but the hydrogen deficiency has an effect in the oxygen destruction rate. As a result, both the energy diffusion, flux, and heat release are reduced, as is highlighted in figure F. The distributions for the region with negative curvature follow the opposite trend. In graph C, the temperature profiles show that in the region with positive curvature, the equilibrium temperature is smaller than the temperature of the planar flame. The region with negative curvature shows the opposite trend, in which the temperature gradient is greater than the planar flame. The effects of flame curvature, normal, and tangential strains in the flame stretch rate and flame displacement speed were studied using DNS for slot burner flames of two fuels, methane and DME, at stoichiometric condition and phi equals to 0.7. So our considerations so far are: the strain and curvature contributions to the Karlovitz number have the same intensity in the region of positive curvature, but the curvature contribution becomes strongly negative and dominant in the concave curvature region. The stoichiometric flames present stronger variations of Karlovitz number when compared to the Ling flames. The correlation with Karlovitz number is similar for both fuels and equivalence ratios, since both fuels hold stable flames. The mass fraction of hydrogen along the flame surface presents strong deficiency in the positive curvature region and strong excess in the negative curvature region when compared to the planar flame. So for now that's it. More results and details can be seen in the paper. And thank you for your attention.